So this is a question that makes me lie awake at night. I'm like, absolutely, I'm just about to fall asleep and I wake up screaming and I go, when is a function differentiable? Now come on, tell me, when is it differentiable? And I have to sit and think it through, all right? And such is the life of a maths teacher. Not. Okie dokie. Hi guys, welcome to this lesson today on differentiability, or when is a function differentiable? And we've actually already touched on this in a previous lesson or video. So a recap is always a good way to start. If you've pretty much completed all the work in differentiation as such, all work can now be assessed on your SAC. How exciting is that? Right, those of you who have no idea what a SAC is, and it sounds incredibly rude if you're in any other part of the country, or in fact the world other than Australia, a SAC is a pretty full-on assessment here. It's part of the exam, and it's quite a stressful event. So those of you who are being taught by me, hey, don't worry about it, it's not that stressful, it's all good. Right, so last time we've looked at the idea behind continuity, or what makes a function continuous at point, and now we're going to look at differentiability of points. This is one of those questions that will end up in an exam. It will be written really weirdly, and it will be worth undoubtedly 1, 2, 3, 27 marks. Okay, it's one of those tiny things that you really do need to make sure you understand. So let's do this hybrid function as a recap. Remember, this hybrid function is a way of writing a graph, or writing all the different components of a graph in one way. So if we look at this graph here, as we notice, it seems to be a little bit disjointed. It kinks at the point 0, 0, a great band, the kinks. And so what we have is the graph is x for x is greater than or equal to 0, and negative x for x is less than 0. And remember, you can't have both greater than and less than or equal to. On both of those, it can only be one. So all it does is it describes that for all values where x is greater than or equal to 0, we have the equation y equals x. And here we have the equation y equals minus x. And because they're straight lines, that is great, because we know that y equals mx plus c for straight lines. So the value in front of the x is my gradient. And so without too much thought, I can write down the gradient here is minus 1, and the gradient one is 1 here. Yes. Now remember, at this point here, they share a common value, all right? That's not strictly speaking true. But what we do know is, if I put 0, if I do f of 0 into both of those equations, what do I get? I get 0 and I get 0. So I suppose you could argue they do share a common point. But the point of it is it differentiable there? Well, firstly, it's continuous. And remember, to be continuous, f of x has to be defined at x equals a. All right, so that means that as for it to be defined at a point, there actually has to be a point there. So f of 0 in this situation has to be equal to 0. And it has to say that as we move closer and closer to the value of a, in this case, or the value of 0, that the function of x gets closer and closer to the f of 0. So basically, to be continuous, it just means that as you get closer and closer to here, and as you get closer and closer to here, and you look at your y values, are the y values converging at the same point? Are they getting closer and closer to 0, depending on which side of the line you come to? Hell yes, they are. And so in this situation, the graph is continuous. I'm not going to do too much more. That was all done in the previous video. So as I've done before, if we were to draw the graph of the gradient function of that hybrid function, and f of x is equal to x for x is greater than or equal to 0, or minus x for x is less than 0, then remember we have the gradient for this one here is equal to 1, and the gradient for here is equal to minus 1. So here is my straight line, y is equal to 1 for all values greater than or equal to 0. Or in fact, now we're actually going to say greater than 0. Actually, I'm going to write that as greater than 0 for what I'm about to come to. And this is y is equal to minus 1 for the values of less than equal, so equal to 0. But at this point here, and at this point here, we have an issue. Because for it to be differentiable, we have to make sure that as the gradient, likewise with continuity, as the value, as I get closer and closer to the point, or to be any point, then I have to make sure that the values of the gradients are going to converge to be the same value. And unfortunately, they're not. If I was just to choose, if this is my point at 0, and I was to go infinitesimally in, At this point here, the gradient is 1. At this infinitesimally point closer, it's -1. They are not going to converge on anything. They're not getting closer and closer to anything. All right. Whereas if I was to take this point here and look at my x values from the right-hand side getting closer and from the left-hand side getting closer, the value is always 2, 2, 2, 2, 2, 2, 2. They're getting, obviously, 2, 2, 2, 2. So they are converging to be the same value. That was a really silly example with those straight line. But anyway, so at this situation here, contrary to what this graph has seemingly shown, I should have open circles at that point there because it's not differentiable. Now, you don't always have to have the graphs of the gradient functions to find a point to do. You don't always have to draw them. All right, you don't have to draw them. You can do tests by actually just using hyperfunctions and differentiation. So, for example, here is my function. It's given me that for greater values, for x is greater than or equal to 0, we get x squared minus 3x plus 2, and for x is less than or equal, we get minus x plus 2. So this is obviously part of a quadratic, and this is part of a straight line. The checkpoints say, check where the functions meet. Well, they meet at x equals 0. Right? So it would appear from here that their meeting point is x equals 0. That's point number 2. Find the value of function of x at the point they meet. So when I put 0 into both of those equations, what do I get out? So that's what this means. I put 0 into both of my equations, what comes out? What comes out? Well, 2 for both of them. So as they both have the same value, it means as I'm getting closer and closer to the point 0, and here's a really rough sketch, I have no idea what it looks like, but here is my point 0. As I get closer and closer here, and closer here, my y values both from the left and from the right of the point are coming closer and closer and will meet at the point 2. So that's good. It's continuous. Thank you very much. We're much happy. Very happy, very happy. Now we need to check to see whether it's differentiable. Oh, look, there's the graph. So just in case you're interested, there's the graph. Those of you who want to know how to draw hybrids using Desmos, just put this function in here. All right. So for some reason with Desmos, you do your curly brackets first. X is greater than or equal to 0. Then you do a semicolon. And then you put the function x squared minus 3x plus 2, and then you put a comma, and then x is less than 0. So you're actually putting the sort of the limits first. You're putting the domains first, and then you're putting the function in curly brackets. Just awesome. Just awesome. And as we say, as I get closer and closer to my point here where they join, and my point here from the left and from the right, we notice that the values of the y gets closer and closer to 2, and hence they meet at 2. Now we need to check to see whether the point that they meet is differentiable. And the same idea as continuity. As we get closer and closer to the point, do we see that the gradient values start to converge on a single value? So if we were to differentiate our functions, we get the first one, 2x minus 3, and the second one we get -1. Ooh, interesting. So when we now substitute a point in, and we already know that they meet at the point x equals 0. So when I put 0 into this, I'm finding the value of the gradient at that point. And that's what we're trying to do. We're trying to find out, is the gradient at that point the same? So I've put 0 in because that's where they meet, and out comes -3 and -1. And because these are not the same, the point at that value is not differentiable. Right? So that's really, really important. And here is the graph of the differential function. So here's x, and here is f dashed at x. And this is one I already created earlier. That, if you remember, is the section of the graph that looks like that. Well, we know that's a straight line, so we're looking at y is equal to -1. And because this side of the line, the original function was a quadratic, then we know that when we differentiate that, we're going to end up with a straight line. And as we can see, and again, my graph didn't do the open circles, but I would have to put open circles on there. And don't forget to label that as 0, -1, comma, -3. Right, that's really, really important. Now, something to note and be really, really important to note is that if a function is differentiable at x equals a, then it has to be continuous. So again, let's just draw some standard graph here. There we go. That point there is, if I take my gradient either side of that, then I can see it's going to converge on a single value of the gradient at that point. All right, so whether I go from the left or from the right, it will get to the same value. And we also notice, therefore, that the point must be continuous. But we notice that here, oops, that's a really bad graph. Here, at the point 0, 0, it was continuous, but it was not differentiable. Really interesting question, a really interesting point there for an exam. Right, hopefully that made perfect sense. Hopefully it was not as clear as mud, or was more useful than a chocolate teapot. If not, well, I've done my best. Thanks very much for watching. I look forward to seeing you next time. It's been so great having you watch this video that I'd like to see you again and again and again. Wow, we could make some amazing maths together. So, if you'd like to, and you'd like to be updated as to when I upload new videos, why not subscribe by clicking the button on the right? Otherwise, if you want to click and see another video created for this type of series, then click the video on the left. All right, well, you have an awesome day, and I look forward to see you again.